let's barge in. First topic of this week is repeated roots. So we're taking a second order linear homogeneous ODE, we're building the characteristic equation, we find that the characteristic equation has repeated roots, so two real roots that are the same, and we're going to try to see what happens, what is the fundamental set of solutions in this weird case. So just a reminder, second order linear homogeneous ODEs. How are they structured? Well, second order means that the highest derivative we have is the second derivative of y. Linear means that the terms that we have, all the terms that we have, are functions of x possibly, but the structure with second order will be something depending possibly on x multiplied by y second, plus something possibly depending on x multiplied by y prime, plus something possibly depending on x multiplied by y. We also have homogeneous, that means that all of this must be equal to 0. We are also restricting to the case in which the coefficients of our linear ODE are not depending on x, so they are just values, not functions. And in this case, we assume that the solution has the shape of an exponential of time, and plugging this assumed solution inside our ODE retrieves this function in time and in r. There are two things we don't know in this equation. We have a r squared exponential of r times t plus b r exponential of rt times c exponential of rt. Here the exponential of whatever is different than 0, so we can cancel that out, and we go back to the characteristic equation. A r squared plus br plus c equals to 0. And this is second order equation, so we can solve it by hand in all situations, and we solve it for r. So we have that r is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. This is the standard formula for parabolic equations. In the first case, we have distinct real roots, so the determinant b squared minus 4ac is bigger than 0. And the fundamental set of solutions for this case is exponential of r1t or exponential of r2t. So the two exponentials of the two different roots. So as we have seen last week, then the general solution will be the sum of these two exponentials, each one with a different coefficient depending on the initial condition. The second case that we also saw last week is when the determinant is negative. So we have complex roots, but they're distinct. So we have the roots being constituted of a part that is real and a part that is imaginary and that switches sign between the two roots. Then a fundamental set of solutions is the exponential of the first root times time and the exponential of the second root times time. And the general solution has the same shape as when we had real distinct roots. But we don't like this way of looking at things because it involves looking at things that are complex. And when we look at physical situations, having a complex solution for something that should be completely real is problematic. So we'd rather transform this into something that is fully real. So we can rewrite the exponential of a complex number into the exponential of a real number times sine and cosine of the complex part. So our fundamental set of solutions is exponential of the real part of the solutions times t multiplied by the sine of the complex part times t, and the exponential of the real part times t times the cosine of the imaginary part times t. So our general solution will be the sum of our two fundamental solutions with different coefficients in front. So it's c1 exponential of mu t times sine lambda t plus c2 exponential of mu t cos lambda t. So now we get to the third option. What what happens when the determinant of our ODE is equal to 0? So we have b squared minus 4ac equal to 0. That means that we have r1 equals to r2. We only have one root. So if we keep on going as we did before, then the exponential of r1t is equal to the exponential of r2t. We don't really have to do the Wronskian for this case to see that it would be 0 all the time. This is not a fundamental set of solutions. Can we find, so we found one solution, definitely. Can we find the second one such that the two of them constitute a fundamental set? This is the trick. Because b squared minus 4ac is equal to 0, we can actually write explicitly what r is in this case, and it is minus b divided by 2a. So our first solution is exponential of minus b divided by 2a multiplied by the time. Can we find the second solution? The first step we do is that we assume that the second solution is something multiplied by the first solution. Now, in general, if you have complete flexibility on the multiplication element, so v, any function can be written as the multiplication of any other function times something. The fact is that something can be very ugly. But in this case, we will see that this new unknown function is actually quite easy. So we can solve for this function v, unknown, in a fairly easier way than solving for y2 without any other restrictions. So we are trying to have the information we already have about the solution, in y1, be a stepping stone for us to find the second solution, y2, in an easier way than just starting from scratch and starting from no information at all. So now, instead of looking for y2, we're looking for v such that v times y1 is a solution. What equations does v satisfy? So we're expecting y equals v times y1 to be a solution. We know y1, that is exponential of minus b divided by 2a multiplied by t. That means that we know the derivative of this solution. So the derivative of v times y1 is v prime times y1 minus v times y prime. So that is v prime exponential of minus bt divided by 2a, all of it minus 2b divided 2a, v multiplied by the exponential of minus bt divided by 2a. And the same we can do with the second derivative. It's a bit more complicated, it has a bit more terms, but you know that the product of two functions, when you take the second derivative of a product of two functions, is the second derivative of one function times the second derivative of the other times the first, and 2 times the derivative of the first times the derivative of the second. And this is what is written here. We have y second is equal to v second exponential of minus bt divided 2a minus, the 2 simplifies away, b divided a, v prime exponential of minus bt divided 2a plus b over 2a squared, v times exponential of minus bt 2a. We retrieve the function we want to solve, that is a y second plus b y prime plus c y equals to 0, and we plug all this derivative that we just calculated inside it. Now it might look like a huge blob, but you first should be noticing that everything is multiplied by the same exponential. And then if we wiggle things around, we should be able to solve it a bit more. So we cancel all the exponentials away. Now that we have taken away the exponentials, we have a structure that is a multiplied by something plus b multiplied by something plus cv equal to 0. We want to reshuffle it in such a way as to have sections depending on which derivative of v we are computing. And if we write it like this, we notice that we have a v second plus minus b plus b v prime plus a block depending on v equal to 0. That means that the term with v prime disappears. That means that this is a second order ODE, yes, but it only has second order terms and first order terms, and it's linear. But if we look even closer, we remember that because we're solving for repeated roots, b squared minus 4ac is equal to 0. That means that the term in front of v is actually equal to 0. That means that our equation simplifies to v second equal to 0. That is just a linear dependency on time. So v is equal to c1 plus c2t. Going back, we remember that that means that our solution, the second solution that we wanted to find, is compounded of c1 multiplied by y and c2t multiplied by y. So our full solution is c1 exponential of minus bt divided 2a plus c2t exponential of minus bt divided 2a. You may notice that in this case, t exponential of minus bt divided 2a is the term we added, while the exponential of minus bt divided 2a was already there from the previous thing. So we can simplify a bit and saying that the fundamental set of solutions is the initial solution that we found from the repeated root, so exponential of minus bt divided 2a, and the new term that we got from doing all these steps in v. So we just solved and we got t multiplied by the same exponential. So t multiplied by the exponential of minus bt divided 2a. Let's check the Bronskin. Do the two elements that we have found until now actually have a Bronskin that is different than 0? So we take exponential of minus bt divided 2a and t exponential of minus bt divided 2a in the first line of our matrix, and in the second line of our matrix we take the derivative of the first line. So the first element is minus b divided 2a times the same exponential, and the second thing is 1 minus b divided 2a of the same exponential. And if we do all the elements, then some terms cancel out. There is actually a t missing in the lower right corner. But the point remains that if we do the calculations correctly, not as I did, we retrieve that the Wronskian is an exponential of something times time. That is different than 0. So the Wronskian is telling us that the two solutions that we found, the exponential and t times the exponential, are linearly independent. That means they span the full space of solutions. Let's go and try to make an example. We have y second minus 2y prime plus y equal to 0 with some initial conditions. So y0 is equal to 1 and y prime 0 is equal to 2. It is a second order linear homogeneous ODE. It has all the characterization for that. So our first step is to construct a characteristic equation. In this case, a is equal to 1, b is equal to minus 2, and c is equal to 1. So our formula for the characteristic equation becomes r squared minus 2r plus 1 equals to 0. And we solve for it, and we retrieve that 1 is a repeated root. So our characteristic equation can be written as r minus 1 times r minus 1. In this case, then, through the steps that we did before, the fundamental sets of solutions is exponential of t, so exponential of the repeated root times t, and t times the same exponential. That means that the general solution for this equation is c1 exponential of t plus c2t exponential of t. And now we want to fit it in such a way that we find the two coefficients c1 and c2 to have a unique solution. So our first information is that y at 0 is equal to 1. If we compute y at 0 with our formula, c1 exponential of 0 plus c2 times t, so times 0 exponential of 0, we retrieve c1. So that immediately gives us c1 is equal to 1. We do the same trick with y prime at 0 equals to 2. Y prime and of the general solution is c1 exponential of t plus c2 multiplied by exponential of t plus t exponential of t. So we have y prime at 0 is c1 plus c2. c1 is already known to be equal to 1, so c2 must be equal to 1 as well. So to compose a solution, we have that y, the solution of our ODE, with initial conditions, is exponential of time plus time exponential of time. We can check this by computing the first and second derivative. And the first derivative of exponential of time is exponential of time. And the first derivative of t exponential of time is t exponential of time plus exponential of time. So the first derivative is 2 exponential of time plus t exponential of time. And the second derivative, in a very similar way, retrieves 3 exponential of time plus t exponential of time. We take this, we plug it in our ODE, that is y second minus 2y prime plus y, and it does simplify everything out. So this is indeed the solution of our ODE.